We already talked about finding the area under a curve and that telling you the total accumulation of change. And we did that just geometrically. We looked at it and, found triangles and rectangles and stuff. The problem is most curves or most functions don't make nice triangles and rectangles. So the goal here is to standardize that calculation. So here's our process. First, we're going to divide the area into rectangles. And because rectangles are easy to work with. So I'm just going to slice this up into a bunch of rectangles, like so. And you might be thinking, well, those aren't rectangles. You're right, these aren't rectangles. They're just kind of sort of rectangles with weird rounded tops. So we'll talk about that in a second, but let's just pick, just level them off so that they're like rectangles. So we get something like this. It's sloppy, but you get the idea that, actually, let me draw that cleaner so it's easier to see. We'll pick our values at one side or the other. I was just being sloppy here. So we'll do something like this. So we'll just go up, and on the left side, we'll go until we hit the function, and we'll make that a rectangle. This isn't a perfect approximation, but we're not trying to make a perfect approximation. We're just trying to make one that's good enough. As you can see that, this is kind of good enough for now. It's a bunch of rectangles with individual areas. So next, calculate the area of each rectangle. So how wide are these? Well, there's some, amount of delta x wide. We don't know how much, but it's some amount of delta x. And what's the height? Well, the height is determined by f of x. So whatever this point is right here, that f of x determines the height. So the height will be f of some x. So in other words, I've written this so that no matter what my curve is, I can use that curve to find the height, and then I can just divide up and figure out how wide my rectangles are, and that will give me my delta x. So I can always find the area of these rectangles if I know this function. And then lastly, we just add the rectangles together. And this will give us an approximation. Again, it's not perfect, but it's an approximation. And it doesn't involve us trying to figure out what shape will fit best or trying to make it look like something else. It will always work because we can always just use f of x and some width delta x. Now, the accuracy or the precision of that is going to depend on a number of factors. And that's where we're going to talk about the types of Riemann sums that we can do on this next slide. So the types of Riemann sums that we can have. You can have a left-hand sum which sets the height of the rectangle at the leftmost x value. You can have a right sum which does the same idea, but with the rightmost x value. So in other words, the biggest or smallest x. Start it on the left side or start it on the right side. Midpoint is the same idea, but instead of choosing the left side or the right side, you pick the number halfway between the left and right side. Trapezoidal sum is a little bit different. You use left and right values to make a trapezoid, which, if you're wondering, effectively averages them. We also have lower sum, which is to use the smallest f of x on the interval And you can also use an upper sum, which is to use the biggest f of x on the interval. So I'm going to illustrate these in a second, but before we get to that, I want to point out that these two right here, wow, that was sloppy. Let me redraw that bracket. These top two here, left sum and right sum, these are the ones that mainly come up on the AP test. Trapezoidal sum sometimes comes up, and it's useful to know. The rest don't tend to come up, but they could theoretically come up, and they're good to be aware of them. The good thing about the left, right, and trapezoidal sums, actually the first four, left, right, midpoint, and trapezoidal, you can write a generalized equation for those. Lower and upper sums, you can't always write a generalized equation because you kind of have to know what's happening with the function in a given region. So let's take a look at these. So this first one is a left-hand Riemann sum. And you can tell that because the leftmost value on that interval is where we set the height. So the left side of the rectangle touches the function. A right-hand sum does the opposite. The right side sets the height of the rectangle. So where the right-hand side hits the function, that's where you put the height. Then we've got a midpoint, which similarly, you look for the point halfway between take your halfway value and you set your height there. And then trapezoidal, it's a little hard to see, but you basically connect the two ends with a straight line. And that's where you get your trapezoid, because you connect the left side with the right side. And you can see that these have varying degrees of accuracy. Generally speaking, trapezoidal will be your most accurate, followed by midpoint, and then left and right hand, it's kind of up in the air of which of those is going to be more accurate. Then lower sum, you can see that they pick the smallest value in the range to set the height. So you'll notice that the rectangles are always less than, they never poke above the function. Likewise, the upper sum picks the biggest value on these ranges, and it always will poke above the function. And you'll notice on the lower and upper sum, they switch left and right side depending on which end's bigger. And if there was, for whatever reason, the midpoint was the largest, it would pick that as well. Like I said, it's mainly going to be left hand, right hand, and trapezoidal that you have to worry about, but it's good to be familiar with all of the others. So the last idea here is that for a monotonic function, left and right Riemann sums will either overestimate or underestimate. So monotonic means always increasing or always decreasing. And they'll either overestimate or underestimate. So if you have an increasing function and you do a left-hand sum, you can see how it's always going to be less than the function because it's always going to have those gaps in it. If you do a right-hand sum, you'll see that it always overestimates because, you know, it's always pointing above. The reverse is true for decreasing. So if it's increasing, left-hand sum will underestimate. Our right-hand sum will overestimate. And this makes sense because the right values, the values farther to the right, will be bigger because it's increasing. The values farther to the left will be smaller because it's always decreasing. And like I said, for the flip side, if it's decreasing, left-hand sum will always overestimate. Just imagine flipping that around. Right-hand sum will always underestimate. So you'll get questions like this on the AP test where they might say, calculate a Riemann sum, a left-hand Riemann sum, is it an overestimate or an underestimate? All you have to say is, because this function is always increasing or decreasing, and it's a left-hand sum, I know it's going to over or underestimate, whatever the case is.